Hello everyone, welcome to Physics Teacher. So in this live stream, we're into second semester and we're into tests again, and I've got a grade 12 physics course this semester, and we've got our first big unit test coming up that is on forces, circular motion, so it's the dynamics unit test. Okay, so I'm going to go over different questions that I've pulled from different tests that I've used in the past. And since this is a live stream, if you have any questions, please let me know in the chat. That's why it's a live stream. Okay. Otherwise, enjoy, and I hope this helps. So the first three questions that we're going to do, they are true and false questions. And I pick ones that I kind of like for this live stream. So the first one, the sum of all forces acting on a stationary object is the same as that acting on an object in uniform motion. I like this one because a lot of people say false, but it's true. This is true. Let's talk about why it's true. It is true because it says uniform motion. If you remember Newton's second law says the sum of all forces equals mass times acceleration. It does not equal mass times velocity. It equals mass times acceleration. So you probably couldn't see me write that because my screen is in the way. Let me write it over here. Sum of all forces equals mass times acceleration. Okay, so uniform motion means no acceleration. If an object is at rest, it is also undergoing no acceleration. So the net force in both cases would be zero. So they would be the same. Our answer is true. Okay. Is everyone hearing me okay? Everyone in the chat? I think my chat is working, but nobody has said anything yet. But you guys are usually pretty quiet anyways. Number three, the same forces act on two objects having different masses. Okay. The more massive object will experience the greater acceleration, provided the forces are not balanced. Okay, so if the forces are not balanced, you have acceleration. Now, if the force, the net force, is the same, then depending what mass is, if we rearrange this, acceleration equals net force divided by mass. So the more massive object will have less acceleration because it's an inverse relationship, not a greater acceleration. The more massive object will have a lesser or a smaller acceleration. This one is false. Okay, and you can kind of imagine that if you were to apply a certain force onto like an empty box compared to the same force on a refrigerator, you can get the box to accelerate a lot faster, not the refrigerator. Number four, an object's weight depends on the strength of the gravitational field it is in. Yes, it does. An object's weight is not its mass, it's the force of gravity acting on it. That's what weight is, and that equals m times g. G is not a universal constant. We typically use 9.81 newtons per kilogram, but this does slightly vary with latitude, with altitude, locally. Okay, the Earth is not perfectly spherical with its mass evenly distributed everywhere around. Right? It's not that perfect, so it does vary. Okay. True. True. Any questions so far? Why does it say I have to sign into chat? No. Anyways, I don't know if I can view questions right now if you put it in the chat. I'll just keep going. Number 15. An object sits at rest on a ramp. Okay. As the angle of inclination of the ramp increases, so let's look at what that means. So here we have, There we go. So here we have a ramp. Okay, with some angle of inclination. So as it increases, so as it gets more and more and more and more steep, the object suddenly begins to slide. So you have an object on here. It's initially at rest, but as it becomes steeper, it begins to slide. That makes sense. Which of the following explanations best accounts for the object's movement? A. The coefficient of static friction has decreased sufficiently. This is a trick. Okay? No, the coefficient, okay? The coefficient does not mean the force of static friction. The coefficient is that mu value, mu s, okay? And it is only dependent on the two surfaces that are in contact. That's it. It's not dependent on how much contact there is. That would be the force of static friction. So this one is no. B, the force of gravity acting on the object has increased sufficiently. No, I don't know why the force of gravity would be changing throughout it. The force of gravity is going to be the same. I mean, how big is this ramp really? I'm assuming it's not going into space. So no, absolutely not. The component of gravity along the ramp has increased sufficiently. Okay, so let's look at that one. So gravity is always acting straight down. Now, if we split that up into components, one perpendicular to the ramp and one along it, okay, as you increase that angle, that component along the ramp, yes, that will get bigger. Okay. Let's look at the other options. The friction has decreased sufficiently while the normal force has remained unchanged. Oh, so close. The frictional force, yeah, that would have decreased, but it would have decreased because the normal force decreased. So no. And lastly, the normal force has increased sufficiently. No. This is your normal force. It is going to balance with this component of gravity here. Okay, so your component of gravity that's perpendicular to the surface. So that is going to be decreasing. So no. So our answer is C. Okay. Any questions? I don't know why it's asking to sign in. Let me just quickly type in my sign in here. See why I don't have access to the chat. Need to verify my account. Okay, I think I'm in the chat now. Let's see. Hello. There we go. So does anyone have any questions? I think the chat's working. Nope. All right then, we move on. Let's try some other problems. All right, question 7. I like this one. Well, I like all the ones that I've chosen. Hold on, question. Hi, I just started your grade 11. Would this be posted on your site for later? Yes, so all my live sessions you can access later. You can even go onto my channel and on my channel's page and just select live, and you can see all the ones I've done previously. And I've also done some for grade 11 as well. So yes, you can access later. And thank you. It's very nice. Okay, question 7. Free body diagram of a car in a skid. So that means the wheels are no longer spinning. So we've got kinetic friction here. With its brake locked up is best represented by. All right. So let's look at each one. Well, actually, I want to look at first any one that has an applied force. My question would be, what would the applied force be? A lot of students like when a car is moving forward, They need to have an applied force to explain why it's moving forward. But you don't need to have any type of force in the direction of motion. Right? Because remember, Newton's second law says force, specifically net force, affects your change in motion or your acceleration. So if you're moving forward and you hit the brakes, right, your net force is backwards because you're accelerating backwards, right? You're slowing down, right? You don't need a forward force in order to slow down. So I can tell you right now, none of the ones with applied force. So we're kind of left with option A. But let's go over that. You, of course, got gravity and the normal force, but then you only have kinetic friction because the wheels are locked, so the tire's skidding against the ground. That's a motion between the surfaces, so kinetic friction. The answer is going to be A. All right, number 10, a lot of students sort of overthink it and they start getting confused. But it was meant to be quite a simple, quick question. Yes, you'd have to use your calculator for this one, but it was meant to be quick. So let's look at it. Forces 2.4 newtons and 1.8 newtons act on an object at right angles to each other. So you have one like this. Let's make that one 2.4. It doesn't matter what direction you make it, as long as the other one is perpendicular to it. So it's easy just to make right and up. 1.8. What is the magnitude of a third force acting on the same object so it remains stationary? Okay, so for it to remain stationary, we know that the net force must equal 0, just like one of the previous questions that we talked about. So if the net force is 0, that means that all these forces, let's call them force 1 plus force 2 plus force 3, must be 0. So rearranging, you can get force 1 plus force 2 is equal to negative force 3. But we don't even need to consider the negative because it's only asking for the magnitude. So we can ignore the direction completely and just say, okay, we have this one, which is 2.4, connect with this one, which is 1.8. The other one must go right back to 0. So it's just asking, what's the hypotenuse of a triangle whose sides are 2.4 and 1.8, and it's a right angle triangle. So all we're going to use is Pythagorean theorem, where the force we're looking for, or the magnitude of force 3, is just going to be the square root. So we got a squared plus b squared equals c squared. So we have the square root of 2.4 newtons squared plus 1.8. And like I said, can't do this one in my head. So I'm going to whip out a calculator. Square root of 2.4 squared plus 1.8 squared. 3. Oh, that's nice. Okay, 3.0. That worked out really well. So our answer is going to be C. It's always satisfying when an answer works out to such a nice number. Any questions? Okay. The next one sometimes bothers students. Says, which of the following units is equivalent to a Newton? And students think they have to memorize this. It's not something you have to memorize. Just look at the equations. Right? Most of my students get an equation sheet. They don't have to memorize many equations, but this is a Newton. Out of all the equations you do in physics, I bet you have F equals ma memorized. Right? Newton's second law. F equals ma. We're not going to worry about writing all the subscripts here. So force is in newtons. Okay, so let's just write the units. Mass is in, well, kilograms. Am I writing too low? I think I'm writing too low. Let me see here. Yeah. Okay, so let me just write this to the side then here. So force is in newtons. Mass is in kilograms. And acceleration is in meters per second squared. Okay, so the first one is kilograms meters per second. No, if that were true, Newton's second law would be F equals mv, which it is not. So no. Second one, kilograms, meters per second squared. That's the one. Actually, that was D. The second one was grams. No. Centimeters, no. That's not SI units, meaning our standard international units. So no. And centimeters, no. Okay. Answer is D. Okay, but just look at your equations. It's called dimensional analysis. So you look at your equations, put your units in, and then you can rearrange your units just like you would rearrange an equation. So, for example, in this case, I could divide by kilograms and say, well, a Newton per kilogram is equal to meters per second squared. This is why sometimes we write G, we call it the acceleration due to gravity, and we say 9.8 meters per second squared. Whereas other times when we're dealing with forces, we call G the gravitational field strength, and we say newtons per kilogram. You can see those units are equivalent. We just change it depending on sort of like the context of what we're talking about. All right? Any questions? Okay. I have questions. I have more questions. We got lots to go. All right. Moving on. The orbital radius of a satellite circling the Earth. Here's a big one. Okay, so if it's circling the Earth, this is a circular motion question. Okay. Oh, I'm getting things coming up in the chat. Oh, I think those were old texts saying the chat's not working. I think it's working now. So, circular motion, we have an object orbiting the Earth. So what we can do is analyze our circular motion. Say, sum of all forces contributing to centripetal or circular motion is equal to mass times centripetal acceleration. And if you have a satellite orbiting the Earth, the only force that contributes to that is gravity. So we have gravity, which we're going to use universal gravitation. G, I like to use big M and small m, meaning big M, the Earth, small m, the satellite, all over r squared, the distance between their centers, is equal to m, that's our satellite, times AC. Now, since it wants to know, looks like it's talking about speed and all the different options, so we're going to write AC as v squared over r. So mass cancels. So immediately it says the orbital radius of a satellite circling the Earth. If you look at B, it says depends only on its mass. Well, no, mass just canceled. That one's definitely not true. The orbital radius, so if we rearrange for r, we can cancel 1r. Okay. Depends only on its orbital speed. Okay, so we've got v in there. Depends on both its orbital speed and its mass. No, mass canceled. Is the same for all satellites. No, you can put satellites at different orbital radii, so no. Is directly proportional to its orbital speed. No, right? If you looked at this, you can see that v, these are going to be constants. We have the universal gravitational constant and the mass of the Earth. So if we look at proportionalities, v squared is inversely proportional to the radius, meaning the slower out you go, not the slower out you go, the further out you go, the slower you're moving. I was like combining my sentences in my head there. Right? So it's not directly proportional, it's inversely proportional. Okay. So it depends only on the orbital speed. I don't think we need to say it depends on the Earth's mass because we are orbiting the Earth. So that's kind of a given. Okay. Any questions? Oh, you couldn't see me write that. Let me just rewrite what I did here. V squared is proportional to 1 over r. That I just got from here. V squared is inversely to radius. So I just wrote it as a proportionality. That's not an equation, it's not an equal sign, but it just shows how one thing changes with another. right? So as v gets bigger, r gets smaller. This is actually interesting because if you have something in orbit, usually we always say, I'm going on a tangent here, but tell me if you want me to stop. Usually I always say drag and frictional forces, things like that, slow you down. But in this case, it's actually going to speed you up. If you have a satellite that has a decaying orbit, let's say it starts to hit a bit of the atmosphere does remove its energy and its orbit decays to a lower orbit. Because it decays to a lower orbit and r is decreasing, v actually increases. Right? So its velocity is starting to increase as it's decaying to a lower orbit because of this relationship, this inverse relationship. Anyways, moving on. Question 5. I like this question. Students seriously overthink this one because there's so many numbers in there. A 24 kilogram traffic light is suspended from the midpoint of a cable suspended between two poles. The angle between the cable and the pole is 80 degrees at both poles. The net force acting on the traffic light has a value of. So we've done questions where you have like hanging objects and you have to find the tension in the cables. And not only have we done questions like this in a physics class, but students have done questions like this in the calculus and vectors math course as well. And they're usually quite big problems trying to calculate the tension in the cables. And this is why students see this question like, uh-oh, get out a separate piece of paper, start drawing the diagram, start calculating. But it's not asking for tension. It's asking for net force. And it's saying it's suspended. It's all the information you need. The 24 kilogram, don't care. 80 degrees, don't care. A force of gravity, don't care about anything. If it's being suspended, the net force is 0. That's all you need. Okay? So try not to overthink one like that if you get it on a test. Okay? Students will get nervous, but slow down, read the question, understand the question before you try and solve it. Don't jump to the equations if you don't fully understand what it's asking you. All right. Next one. We have a rock is tied to the end of a string and whirled around in a circle that describes a vertical plane. Okay, so like this, up and down. This would be a horizontal plane. There's 2 types of circular motion questions we typically ask in grade 12. The ones where it goes like this, horizontal plane, and therefore we don't consider gravity because gravity is perpendicular to that plane, and the vertical plane where we do consider gravity. Okay. All right. So, at which position is the tension in the string the least? So, when we're doing verticals, we typically like to look at 2 locations, the top and the bottom. Okay, so at the top, you're going to have some force of tension and force of gravity. And at the bottom, you have gravity down and tension up. So if you're whirling it around in a circle, and in grade 12 physics, we keep constant speed always. We don't have angular accelerations or things like that. We stick to degrees, not radians. Everything's going at a constant speed. So even if it doesn't say constant speed, we can assume that. Okay. So that means since it's moving at a constant speed and our acceleration, centripetal acceleration is v squared over r. R, it's always going to be a perfect circle. We don't deal with ellipses in grade 12. So r is going to remain constant. V is going to remain constant. So centripetal acceleration is going to remain constant. But at the top, we have 2 forces that are acting down. So gravity is helping tension, so tension doesn't need to be so high. So at the top is where tension is going to be the least. So our answer is going to be at the top. At the bottom, if it asks you, because I could change the question, it says, and I could say at which position is the tension in the string the most? Okay, at the bottom, the tension in the string has to fight gravity while supplying that centripetal acceleration. So it's going to be the most at the bottom, the least at the top. Okay? Any questions? No? Okay. We are going to move on to problems. We're going to solve some problems. So I have 3 more questions, and they're all going to be different types of problems. So let's start with this one. So Beanie is a curious dog. Yes, Beanie is the name of my dog. That's why I used that name. He's sleeping right now. Who suspends his toy to the ceiling of the car during a road trip. Let's just ignore how that's even possible. So we just have a toy hanging from a string to the ceiling in a car. Okay. When the car accelerates at a constant rate forward, the string suspended makes an angle of 15 degrees. So it makes some angle of 15 degrees to the vertical. There's the toy. Calculate the magnitude of the acceleration. So let's look at the forces that act on this. So we've got gravity acting down. Call it Fg. Okay, we're going to have some force of tension on the string. Now tension we can split into 2 components. Now if you look at it, from the car's point of view, it looks stationary, right? Which is crazy because you have an unbalanced force acting there. Right? You can have your vertical forces balanced, but you only have one horizontal force, which is this component of tension. And that is because the whole car is accelerating forward. So we can use that component to figure out what our acceleration is for the car. So let's look at our x component, or our horizontal component. Sum of all forces in x is going to equal mass times acceleration. All right, so this is 15 degrees here. So that's the same as this angle here. I'm just going to call it theta. Theta will be 15 degrees. Okay, so our opposite to that, we have force of tension times the sine of theta. So that is our component right here. Okay, and if you're unsure how to do that, remember this is a right angle triangle. So just use your trig ratios. So you can just say sine theta equals, I just called that a star. Okay, so star, which is opposite over hypotenuse tension. So rearranging, you get that component, or star. I've never done star before, but is tension times the sine of theta. And that equals mass times acceleration. Of course, the problem is I can't solve for acceleration because, well, 1, I don't know mass. 2, I don't know tension. There's too many unknowns here. So let's analyze our vertical forces. So in our vertical forces, in y, we know it's going to be balanced, because the car is not accelerating upwards. So this is going to equal 0. And we have this vertical component, which is going to be, it's the side adjacent to theta. So we have Ft cos theta. And gravity is down, and I'll just make up positive. So minus gravity, Fg, is equal to 0. Okay, so let's rearrange this equation. So we have Ft cos theta. If we bring gravity to the other side, it becomes positive. And I could write the equation for that, which is mg. And now what I'm going to do is have 2 equations. I don't want tension, so let's solve for tension and substitute. So tension is mg over cos theta. So if I take that value and substitute it in for tension in this equation, we get mg over cos theta times sine theta is equal to ma. So great, tension is gone, and you know what else? So is mass. And if you're like me and you love trig identities, this is a very simple one, but sine theta over cos theta is tan theta. So we're left with g tan theta equals acceleration. Very simple, very elegant. So g is 9.81 meters per second squared times the tan of theta was 15 degrees. So we get acceleration that I'm going to need my calculator for. 9.81 times the tan of 15. 2.6 meters per second squared, and you could just say forward. How's that? Anyone have any questions? The chat still working? Looks like it. All right then. If no one has any questions, remember you can come back and watch this at any time. It just stays up on my channel. We're going to go to this one, circular motion. So we have a 0.5 gram insect. Rests on a compact disc. That's a CD, by the way. One of these days I'm going to have students that don't know what a CD is, and I'm going to feel really old. Okay, but it rests on a compact disc at a distance of 4 centimeters from the center. So that is telling us radius, and this is mass. But we're going to change mass into kilograms. So divide by 1,000, so we can change it into kilograms. So we got 0. It's going to be small. 0.005 kilograms. All right. The disk rotation rate, the disk rate of rotation, varies from, so it's telling us frequencies, 3.5 to 8 hertz. In order to maintain a constant data sampling rate. What is the minimum value? So we want to know the minimum value of the coefficient of static friction that would prevent the insect from slipping at the, and this is important, the slowest rotation rate. So that means we have information we don't need. It's asking for the slowest rotation rate. That's this. That's the slowest rotation rate. So we're not going to even need that, right? Not all questions give you just the right amount of information. Be careful, some questions can give you more than what you need. Okay, so you have a CD, and we are going to have a little bug. There's a bug. I'm just going to draw a square. We're going to draw a free body diagram. So let's say it's on the CD moving in this circle here. Okay. What's keeping it on that CD? Static friction. So we have the force of static friction always inwards, or center seeking. That's going to be our force that contributes centripetal force. Okay. Then we have gravity going into the screen and the normal force coming out. So this is kind of like a bird's eye view free body diagram. So I'm not going to draw those. They're perpendicular to centripetal force, so they're not going to contribute to that anyways, but we will need them. So what we can do is, that's all towards the center is going to be our positive direction. So sum of all forces contributing to centripetal force is equal to mass times centripetal acceleration. So this only force is Fs. Okay, and it's going to be positive because it's center seeking, equals to m times, so we have different equations for centripetal acceleration. I showed you one before, the v squared over r, but we don't need speed. We want the one with frequency. So the other two are, one is with period and the other is with frequency. So one with frequency is 4 pi squared r, frequency squared. All right, But it wants to know what mu is. So you have to remember, what's our equation for static friction? It is mu times the normal force. So this is what we have. We're just substituting equations into our Newton's second law here. Now this is where I said you're going to need gravity and the normal force. Now they are balanced, right? Our insect's not flying upwards or anything like that. So gravity, which is going into the screen, is balanced with normal force coming out, so that we can say that Fn is going to equal mg. And that is all equal to m 4 pi r frequency squared. We didn't even need to know mass. I didn't have to bother rearranging it. Mass is going to cancel. Divide by g. And we get coefficient of static friction is 4 pi r frequency squared divided by g. So we plug in numbers. So we have 4 pi times r. We do want to change that from centimeters. So that's going to be 0.04 meters. So 0.04 meters. Frequency at the slowest rotation rate. So that's 3.5 hertz squared, all divided by g, 9.81 meters per second squared. You can see your units cancel because a hertz is a per second. So on the numerator, you have meters per second squared. On the denominator, you have meters per second squared, which makes sense because our coefficient is dimensionless. Now we're going to need our calculator. So this is a lot to plug in, so if everybody watching wants to test on their calculator as well, pi squared times 0.04 times 3.5 squared over 9.81. I'm getting 1.97. Okay, but it looks like significant digits. We only have like 2 significant digits, 2 significant digits. So I'm going to write it as 2.0, rounding up. There we go. Any questions? Don't see any questions. Hope the chat's still working. I'm just going to assume everyone's being quiet. All right. All right. Last question. Oh, I'm like scrolling this here. Here we go. Boss level question. So here we have a piece of ice. Mass 500 grams. Let's just say 0.5 kilograms. Slides down the slope of a roof inclined at 50 degrees. It starts from rest. Okay, so that's interesting. Starts from rest. So initial velocity is 0. If it tells you something like that, that's a hint that, in this question, we might also need our kinematics equations, right? Our 5 equations for uniform acceleration. So it starts from rest and slides 8 meters. There's another one. It's telling us displacement, right? So displacement is 8 meters along the roof. Sliding off the edge at a height of 4. Ooh, that's another interesting piece of information. Above level ground. Level ground. That sounds like a projectile coming up. You got 0.62 for the bug question. Let me just quickly go back to that. 0.6. Did you remember to square frequency? I got a lot of students that forget to square frequency. You know what? That might have been my mistake. I just decided to get rid of that square. This square, it disappeared. Square, squared. I did something so many students like to often do. Get rid of squares. So let's try this again. Did you put the square in when you put it? Let me see here. Oh, actually, no. Even though I didn't write it, I put the pi squared on my calculator. So it is 2.0. But maybe that's what you did. Maybe you didn't put in the pi squared because I forgot to write it and my mind was just working strangely. And even though I forgot to write it, I still put it in on my calculator. I did not. There should be a squared there too. There we go. Okay, we're good? Okay. All right, so level ground. Level ground screams projectiles at me, so we might have to analyze projectiles too here. It's all right, we can do this. This is boss level question anyways. We got this. The coefficient of friction, oh, this friction too, is 0.14. All right. Draw a free body diagram. So there's an ABC, because it would be cruel of me if I just started with C, because you need to do A and B to get to that point. So draw a free body diagram of the ice as it's sliding along the roof. Okay, I'm just going to do it right here on the picture here. There's the ice. Okay, it's sliding down, so there's going to be a frictional force, kinetic friction, up the incline. We are going to have a gravitational force, mg, straight down, and we're going to have a normal force perpendicular to that incline. Now, since it's sliding down the incline, I'm going to choose a coordinate system that's rotated. So that's going to be my positive x direction. Always, always, always choose your positive x direction to be the same direction as acceleration. And then, of course, y, you can choose. It needs to be perpendicular to x, but it doesn't matter if you choose that up incline or down incline. I just choose up because it's easier to think of. Okay, that's not all, but any force that is not aligned with my chosen coordinate system, I need to write components for. So I'm going to write components for gravity because gravity is not aligned with my coordinate system. Okay, this angle here is theta. I'm just going to write theta. Theta is our 50 degrees. So those two angles are the same. You can do a little trigonometry there, analyzing these two triangles to see that. Okay, where that's a right angle. Okay, and then I could solve for my components. Not necessarily solve, but write an expression for. So this one's going to be mg cos theta, and this one's going to be mg sine theta. Okay, we got our free body diagram. All complete. Then it says, with what speed does it leave the roof? What speed does it leave the roof? What is that asking us for? It actually wants to know final velocity. I need a kinematics equation, but I only have two pieces of information, initial velocity and displacement. Right? You need three pieces of information to be able to use those equations for kinematics. So what's our third piece of information? Acceleration, right? Remember, forces can tell you acceleration because forces are the cause of acceleration, net force specifically. Now, acceleration is down the incline, so I'm going to do the sum of all forces along that incline, x, will equal mass times acceleration. And I have two forces. We have gravity, or a component of gravity, down the incline, which is going to be positive, and friction, which is going to be negative. So we have mg sine theta minus fk equals ma. Now fk we can expand. We know the equation for kinetic friction. It is the coefficient times the normal force. Okay, so what's the normal force? It's not just equal to mg. Now, there is balance in our vertical components. So you can see this vector is perfectly balanced with that vector. So there's equilibrium there. So the magnitude of the normal force must equal mg cos theta. So continue to expand mg sine theta minus mu k, the normal force being mg cos theta, is equal to mass times acceleration. And luckily, once again, we love it when mass cancels. So there we have an equation for acceleration. Acceleration equals, so g sine theta, so we have 9.81 meters per second squared, times the sine of 50, minus mu k, which is 0.14, times g, so 9.81, times the cos of 50. Right, so there we have our acceleration. Let's try this on our calculators. So 9.81 times the sine of 50 minus 0.14 times 9.81 times the cos of 50. Make sure your calculator, you're doing trig functions here, so make sure your calculator is set to degrees, not radians. And we get 6.63 meters per second squared. Okay. So there's acceleration. But we didn't really want acceleration, we needed it. Because what we want is final velocity. But now that we have three pieces of information, we can go ahead and use our kinematics equation. The one that doesn't have time in it, because we have know nothing about time. But Vf squared equals Vi squared plus 2a delta d. Vi is 0. So square root both sides. We get Vf is the square root of 2a delta d, which we can write as 2 times 6.63 times delta d, which is 8 meters. So we get our final velocity. More calculator work. 2 times 6.63 times 8. 10.3. Okay, 10.3 meters per second. Anyone have any questions yet? Is that good? Okay, I am just going to write on the side here, V final equals 10.3 meters per second, because now I am going to erase so I can give myself some room to do the next parts. The last part, C. All right. Part C says, how far away from the foot of the building does the ice land? Okay, so it is doing this. That's a projectile question, and we want to know the range or the displacement in x from where it gets launched from. Oh, sorry, that's going to be all the way to the building right there. So our displacement in x. So this is our initial velocity for our projectile. Right? The instant it leaves the building, that's the initial velocity for our projectile. And it equals what we just calculated, the final velocity as our, ice? As the ice slid along the roof. Students sometimes get that confusing. Why are you setting initial velocity equal to final velocity? Two separate problems. The first problem was looking at the ice going down the roof. So the final velocity was when it reached the end of the roof. Next problem, projectiles. An ice flies off the edge of the roof with an initial velocity of 10.3 meters per second. So I'm going to rewrite that vector over here. So we have this initial velocity of 10.3 meters per second. Okay. And we can split that up into two vectors because it is at an angle. Okay, this angle here is our 50-degree angle. And that would mean that this angle here is 40 degrees. So you can go ahead and find your components. So the initial velocity in y is going to be, you can use either 50 or 40 degrees. I'm going to use 40. So I'm going to write 10.3 meters per second times the cos of 40, which gives us an initial velocity in y of 10.3 cos of 7.89. And similarly, our velocity in x, I don't need to write initial because for projectiles, grade 12 physics, we don't look at air resistance. So our horizontal velocity does not change. We're not going to have an initial and final. They'll be the same. Is 10.3 meters per second times the sine of 50. Sorry, the sine of 40. Oh. 10.3 times the sine of 40. 6.62. Okay, so let's look at what we know in our x component and our y component. So we know our velocity in x. We do not know our displacement in x, and we do not know the time. So there's only one equation in x, right? And it involves all three of those variables. So I cannot possibly solve for the one I want without time. So I need to figure out the time of flight first. So what do we know in y then? Well, I know initial velocity in y. I do not know final velocity in y. I know acceleration in y. It's 9.81 meters per second squared. And to make things simpler, this is a separate problem from the first set, so I do not need to use that coordinate system. We're just going to use this coordinate system, and I'm going to make down positive y and to the left positive x. So I'll leave gravity as positive 9.8. Okay, do I know time? No, I do not know time, but time is something I want to know. Do I know vertical displacement, how far it falls? Yes, I do. That's 4 meters. So where are we going with this? We have 1, 2, 3 pieces of information. We can use those 3 pieces of information in y to find time. Once we know time, we can find the range. And then we're done. Then we'll be done the boss level question. Okay. Let's do this. So we don't know final velocity. We don't care about that. So this is the equation we want. So VIY times delta t plus 1/2 a delta t squared. Okay, so displacement is 4. I'm just going to leave out units because this is going to be a quadratic. Initial velocity in y is positive 7.89 times time. And we have 1/2 times 9.8. 1/2 times 9.81. I'll do 9.81. 4.905. So plus 4.905 times squared. So if I rearrange this, And if I put it, I forgot the squared. If I rearrange this and I put it in order of what a quadratic in standard form would look like, we have 4.905 delta t squared plus 7.89 delta t. Bring the 4 to the other side of the equation, so minus 4 equals 0. Solve for time. Now you can do this in a couple ways. You can, if you have your quadratic formula memorized, right, you can do like minus b plus or minus the square root of b squared minus 4ac all over 2a. But in grade 12 physics, I am not, and most teachers are not typically grading or marking whether or not you know the quadratic formula. So you can do the quick way if you have a calculator that can do it. Lots of calculators can just do it for you. If you plug in, if you tell your calculator what your A, B, and C coefficients are. If you're not sure how to do that, I have a whole playlist on my YouTube channel for how to use your scientific calculator. You can go find the one for quadratics, and I show you how to do it on a Sharp, a Casio, a Texas Instrument. It's just a useful skill. Okay, so I'm just gonna go, let's do a polynomial. Our A is 4.905, our B is 7.89, and our C is negative 4. Okay, so we get two values. We get delta t as 0.41 seconds, or, what's our other one? Negative 2.0, okay. Negative 2.0 seconds. We don't care about the negative value. There's our time right there. Okay. Oh. Hold on. Sorry, my dog woke up and he was whining. This is Beanie from the other question. We're almost done. Because all we need to do now is find range. And our range equation is just displacement is velocity in x times time, which we know. Velocity in x is 6.62 meters per second, and we found time as 0.41 seconds. So that equals, let me see here. You want to check this for me? .62 times 0.41. 2.71. There we go. 2.71 rounding to 2.7. So 2.7 meters. Okay. Does anyone have any questions? That's the last question from the live stream. If you have any questions, now's your chance. If anyone's writing a test soon, good luck. And remember, you can go back and watch the live stream at any time. No, I don't see any questions. All right then. Good luck on everyone if you're writing a test.